Okay, so this video is pretty focused on solving problems using energy conservation, and we'll focus on energy conservation with gravitational potential and kinetic energy. In this video, in later videos, I'll go over how to incorporate other different types of energies once we learn them and talk about them in class. But for now, we're focused on those two types of energy, kinetic energy and gravitational potential energy. So we have a sample problem here. A 0.01 kilogram penny is tossed down from the top of the Empire State Building, which is 381 meters tall, with an initial downward velocity of 5 meters per second. And then we have these two questions about how high up the penny will be at certain points, and then how fast the penny will be moving when it's about 2 meters above the ground. And just to help myself and to model, I think, what is a good habit when we're solving these problems, I'm going to draw a picture, even though I know I am not artistic in many regards at all. Let's draw this penny. Oh boy, worse with the color in, so I'm going to take that back. And then we'll draw the Empire State Building, which, you know, whatever it looks like, it ends up looking like. I don't know, it's got something weird going on at the top, and here's our building. Not great, it doesn't even matter. But what does matter is that we know this initial height of the penny is 381 meters. And it matters that we know this penny's mass as well. So I'm going to put this 0.1 kilograms in there. .01, excuse me. And the reason that I'm doing this is because when we start working with these like relatively complex systems, and this problem doesn't necessarily represent a terribly complex event or anything, but it's a good habit to get into to create these diagrams, not only for ourselves, but also when we're working in teams or professional engineers and scientists. They really need to be able to communicate the information or the relevant parameters in a problem, or the given information in a problem, in as accessible and easy to understand a way as possible. So even with my bad art, and maybe if I were presenting this to someone else, or if I needed to present this to someone for some incredibly important purpose, maybe that would affect the way that I communicate about this. But for now, just as a practice, this is good enough. So I have our velocity also. I do want to just quickly point out that I'm sort of drawing this as if it's a force, because I know in the past we've worked with free body diagrams and drawn forces and said this is like a force of gravity. Right now, what that downwards arrow represents is not a force. There is a force of gravity acting on this penny. We, of course, know that as it's falling. But what this downwards arrow right now represents is that velocity vector, that 5 meters per second downward that it's going at first. Okay, so we've got this information shown so far. We've got the sort of initial conditions. And now let's focus in then on part A here. So part A asks, how high up will the penny be when it's moving at 40 meters per second? Okay, so I'm going to draw this, and I'll do this in purple, I guess, just because that's what I happen to pick. So let's draw that second part here too. So I don't know exactly where this is going to be, but I'll draw our penny moving somewhere at 40 meters per second. And then the question is, what is the height going to be? And I'm going to put a little subscript A just to remind myself that this is for part A. That's not totally necessary, but subscripts for me and my problem solving, I think it helps me stay organized in those things. So let's try to figure this out using energy conservation. And just as a reminder, what energy conservation means is that the total energy in the system remains constant. So what I'm going to do first, and I'm going to zoom in on this first sort of initial condition, the initial point for this penny first, and let's solve for its different types of energy. So in order to do this, we can solve first for its gravitational potential energy. is mgh. And we'll assume that this is an Empire State Building on Earth and not some other planet or large mass. So we're going to plug in the mass, which is 0.01 kilograms, 9.8, which is our acceleration due to gravity on Earth, that's the g, and then the height is 381 meters. Okay. And now if I calculate that over here, 0.01 times 9.8 times 381. So that gives us 37 point... I'll keep all these decimals for now. I might get lazy later in the video. For now, I'll keep them all. 37.338 joules. Okay, so that's how much potential energy this starts out with. Now let's do the same thing for the kinetic energy. Since we know how fast this is moving, we can calculate that as well. Okay, so 1/2, the mass is still 0.01 kilograms, and the velocity is 5 meters per second squared. Now again, I know I showed this in the video specific to calculating potential and kinetic energies, but my recommendation, if you find yourself making mistakes on this calculation, is to do the squaring of the velocity first. So I'll type in 5 squared, and even though I know that that's going to be 25, it's good practice to check on your calculator anyway, times 0.01 times, and then I'm going to use 0.5 for a half just because fractions are, I think, more difficult to type in on a calculator. And that'll give us this initial kinetic energy of 0.125 joules. So not a lot of kinetic energy at all at first. That makes sense that the potential energy would sort of dominate in this system, since we know a person tossing it down, they might be able to get 5 meters per second on it, probably even a little faster initially. But since it's so high up on top of the Empire State Building, most of that energy is probably going to be this gravitational potential energy. Now, the reason that we're doing this is that if we can figure out the total energy in this system, we can then apply that to parts A, part B, any other parts here along this entire journey, that total energy should remain constant. So that's why we're calculating these different types of energies, and that's what we'll calculate now, is this total. And all I'm going to do, like any other total, I'm just going to add these two things up. So 37.338 plus 0.125, so adding up our kinetic and potential energies, and that gets us this total of 37.463 joules. Okay. So that is going to be a helpful thing for us when we come back down to part A here in purple and try to figure out this missing height here, how fast or how high up the penny will be when it reaches this speed, this velocity of 40 meters per second downwards. So before we do anything else, I'm going to just write that our total energy, let's zoom in a little bit, our total energy still needs to be the same 37.463 that it was before. And we can figure out one of the energies. I see we know the velocity, and the energy that has to do with motion and velocity or speed is kinetic energy. So let's calculate the kinetic energy that we can figure out there. So 1/2 mv squared, and in this case we know the mass still, not changing, penny isn't breaking or anything, 0.1 kilograms, times this velocity of 40 meters per second squared. Okay, so let's see what that gives us. 40 squared, I'll hit enter, times 0.5 or times 0.01 to stay consistent with how I've done in the past, 0.5. That's our half. And that gets us 8 joules as the amount of kinetic energy at this point. So that's a bigger chunk. That makes sense because as this penny falls, it should be gaining kinetic energy and losing its potential energy as it's losing its height, but picking up that velocity. So that leaves us with a question of what is this missing potential energy that's going to get us to the total that we should know. So I know that this kinetic energy plus whatever this potential energy is needs to give us this total of 37.463 joules, right? That's from up here, and that number came from the initial conditions from the penny up here up top. So we figured out the total energy initially in the system. Assuming that this is a closed system, that total energy should stay constant throughout this entire drop of the penny. So saying that this kinetic energy that we could figure out because we knew the velocity, plus this potential energy that we don't know yet, needs to give us that same total, and we can do this at any point throughout the entire drop. And so now it's a relatively quick algebraic problem for us to solve. We can solve for this potential energy just by subtracting 8 on both sides, and that's going to give us, I'll check this in a calculator, but it looks like it'll give us 29.463 joules. Let's check that because I know better than to blindly trust or to trust without checking my mental math. -8, 29. All right, 29.463 joules. All right, that still doesn't quite answer the question because that doesn't give us the height at A, really only gives us the potential energy. And just as a side note, I really could be using subscript A for all of these things. I could have said kinetic energy A is 1/2 mv squared and all these things. And in fact, maybe I will leave that in there now just to sort of emphasize the fact that we're solving all of this for the height at part A, and all of these pieces of information are specific to part A. Now, if we know a potential energy and we know mass and gravity, but we just don't know the height, we can solve that equation using our same potential energy equation that we've used before. So our potential energy is equal to mgh. In this case, that's 29.463 joules. And our mass of the penny is still 0.01 kilograms. Gravity is still 9.8. And then the height is going to be some unknown thing that we're going to try to solve for here. So let's, of course, there are a lot of ways that you could solve this from here. Let's combine our like terms. That's how I'm going to choose to solve this first. I think that'll be 0.098 h. So just combining our 0.01. Let's check that real quick. Yep. And then we haven't done anything with this 29.463 yet. And now to solve for h, we've just got to divide both sides by the 0.098. Cancel that out, and let's see what we get. So 29.463 divided by 0.098, and we find, oh my goodness, it's barely fallen at all. It started up at 381 meters. I guess it's fallen about 80 meters so far. So the height that we found here, 300.64 meters is that height. And why don't I specify that's the height at part A. So that is how high up this penny is going to be once it reaches that speed of 40 meters per second heading downwards. So I could go ahead and replace that HA with 300.64 meters. I'm not going to, only because I am running out of room, and I think that it will end up looking significantly messier if I do. Okay, so part A is now done. Now let's go to part B here. So how fast will the penny be moving when it is 2 meters above the ground? I picked that number because that is about an almost average height for humans. It's rounded up to the nearest full meter, but I was curious how fast this would be moving when it reached like a person's height. Because I don't know if you all have heard that those drops could be potentially fatal. If a penny from the top of the Empire State Building were dropped on you, I could really do damage. So let's say this height is 2 meters. And let's try to figure that out. So we don't know the velocity of this penny. So why don't I include that in our diagram? So I'll just have a little downwards arrow and a little question mark for this velocity, saying that we don't yet know how fast that penny is going to be moving once it reaches about a human head height. So we've already gotten a little bit of a head start here because we already know that the total energy for part A, for part B, for any part of this journey, if it's a closed system, should be the same total of 37.463. So I'm going to go ahead and note that first, that this total still needs to be 37.463 joules. And at this point, we know the height, but we don't know the velocity. So the energy that we can figure out, the piece of this total that we can figure out is probably the potential, because I know that's the one that has to do with height. So let's go ahead and calculate that one. Our potential energy is still just mass times gravity times height. Whoa, what in the world happened with that H? Alright, so we know the mass is still 0.01 kilograms. G is still going to be 9.8 since we're on Earth. And then the height at this point in part B is 2 meters. And maybe I can specify this is the GPE at part B, so I'll add that little subscript just for my own clarity here. Okay, and then we can go ahead and calculate that. So let's just plug this into our calculator, 0.01 times 9.8 times 2, and that'll give us 0.196 joules. Okay, not a lot of potential energy down there. Now what we know still is that this potential energy plus whatever that kinetic energy is needs to give us that total energy of 37.463 that we found initially in the orange part up here at those initial conditions, at the part A in purple, as well as part B, and at any other part of this. So this is where we apply that idea of conservation, when we say that these two energies have to still add up to that same total if energy is conserved within this system, if this is a closed system. And then this is a pretty simple algebra thing. We're just going to subtract, of course, 0.196 from both sides, because right now we're adding on both sides. 0.196. So those go away, and we'll find our kinetic energy. And I should specify that this is at part B as well, is going to be equal to, let's see what this is, 37.463 minus 0.196. And we find that the kinetic energy there is 37.267 joules. Okay, so we figured out our potential energy because we knew the height there and we knew the mass and gravity still. We figured out our kinetic energy by applying energy conservation and using what we knew about the total energy. Now we can figure out this missing velocity, how fast the penny's actually going to be dropping when it sort of reaches around head height for people. And we'll say we know this kinetic energy is 1/2 mv squared, which is using our general kinetic energy equation. And now let's plug in the stuff we know here. So we know the kinetic energy is 37.267 is equal to 1/2 times the mass of 0.01 times v squared, leaving a v for our velocity because we don't know what that is yet. Now if we combine like terms here, or sort of simplify this, that'll give us 0.005 v squared. And we haven't done anything over here yet. Let me check that. 0.1 times 0.5. Yep. And now we're going to divide both sides by this 0.005. And that will cancel out. these, and let's see what that gives us over here. 37.267 divided by 0.005. Oh boy, 7,453.4. And don't forget, all we've solved for so far is v squared. We haven't figured out how fast it's actually moving. That would be just velocity, not velocity squared. So in order to get rid of this squared, we're going to need to take the square root, and we have to do that. If we do it to one side, we've got to do it to the other. So let's take the square root of this 7,453. That gives us 86.33 meters per second is this velocity at part B. So I'll give that subscript for part B. Whew. Okay, well that's pretty fast. That 86 meters per second, that would probably do some damage to my head, I think. Now, in reality, there probably would be some air resistance as this falls, and it's not likely that the penny would actually reach this velocity because there would be that external force to the system of this penny as it falls. But if energy is perfectly conserved, if this is an isolated system, then it would in fact reach this 86.33 meters per second once it gets around our head height. Just to recap what we sort of did in this video, we were trying to apply energy conservation to make predictions for, in this case, a penny at different points of its fall. And the reason that conservation helped us out here was because if we could figure out the total energy anywhere in the system at any point throughout its fall, that total energy had to be the same throughout the entire sort of fall, throughout the entire process. So that's where this, and this came into play, was at part A and part B. The energy, the total energy, had to be the same, 37.463, even though the potential energies and kinetic energies could all be different and transforming between each other. We used conservation to figure out the missing energies at any point, and then figured out a missing height or velocity from there.